theory. There are a few successes of inflation which I think indicate rather strongly that our universe almost certainly did undergo this process. And I don't have time to discuss all of these successes, but I'd like to mention a few of them. The first that I'd like to mention out of three is the large-scale uniformity of the universe, which turns out to be very difficult to understand in the context of conventional cosmology. This large-scale uniformity is seen most strikingly in the cosmic background radiation, which is known to be uniform in its intensity all across the sky to an accuracy of about 1 part in 100,000, which if you think about it really is an unbelievable degree of uniformity. In conventional cosmology, without inflation, we have never found any way to explain this uniformity. In fact, if you imagine that the universe started out not quite uniform and asked what would it take to make it uniform by the time that we're observing it in the cosmic background radiation, one quickly finds that it would require the transfer of energy and information at about 100 times the speed of light. And as far as we know, nothing goes faster than light. So this is strictly forbidden, according to all that we know about the laws of physics. Inflation gets around this problem in a very simple way. Because inflation adds this burst of exponential expansion, it means that in inflationary models, the universe could have started out much, much smaller than we ever could have imagined in conventional cosmology. While the universe was so small, there was plenty of time for it to come to a uniform temperature, really by the same kinds of processes that cause a slice of pizza to cool when you take it out of the oven. Once this uniformity is established on this very tiny scale, then inflation takes over and magnifies this tiny speck to become large enough to include everything that we see. Inflation, therefore, gives a very natural prediction that the universe on the very large scale should really look the same in all directions, which is exactly what we see and otherwise find very difficult to understand. Second success of inflation I want to point to is the prediction that it makes for the overall mass density of the universe, which cosmologists always talk about in terms of this Greek letter omega. We say that omega is predicted to be 1. Omega is actually defined as the ratio of the mass density of the universe divided by a number which we call the critical density. Now, until about 5 years ago, this was a problem when theorists argued with observers about inflation, because the observers always told us that the mass density of the universe was only about 0.2 or 0.3 of this critical density. But now that's changed. In fact, according to the latest data based on the WMAP satellite analysis, we now think that omega observationally is determined to be 1.02 plus or minus 0.02, extraordinarily close to the inflationary prediction of 1. The important new addition is this idea of dark energy, this mysterious material which seems to be filling the universe and causing the universe today to be beginning a slow episode of what is very similar to inflation. Third success I want to point to, and now I'm reaching the end of my talk, is the small-scale non-uniformity of the universe. Although the universe is surprisingly uniform on the largest scales that we can observe, for example in the cosmic background radiation, on smaller scales we of course see a tremendous amount of structure in the form of clusters of galaxies down to planets and buildings even. Where did all this structure come from? Inflation offers the fascinating answer that all of the structure actually originated due to the quantum uncertainty principle. It's due to quantum uncertainties in the density of matter as inflation was ending. Now, normally we think of quantum fluctuations as only being important on incredibly small distance scales, sizes of atoms, nuclei, or smaller. And that's actually consistent with what we see here as well. These density fluctuations were generated at incredibly small scales during inflation, where one would expect quantum physics to be important, and then the inflation itself stretches the wavelength of these perturbations to become astronomical or even cosmological. And the amazing thing is that we can now measure these quantum fluctuations by a number of different methods, as Max was discussing. We measure them, I think, most accurately in the cosmic background radiation, and the most recently highlighted measurements of that type were by the WMAP experiment, the Wilkinson Microwave Anisotropy Probe. There's a picture of Dave Wilkinson, who has certainly been one of the leaders of cosmic background radiation research from the very beginning. Here's the very important piece of data. I guess I'll just ask you to look at the upper slide only, which shows what's called the power spectrum, the intensity of these non-uniformities as a function of the angular wavelength on the sky that you measure those non-uniformities to subtend. The angular scale is shown on the top if you can read it. It's a little hard to read, but in any case, small angles are to the right, large angles are to the left. It's also hard to see that the long wavelength ripples are measured most accurately by WMAP, but at shorter angular scales, the best data in fact does come from the ground, from the Cosmic Background Imager and ACBAR, two NSF-sponsored ground-based observations. And what you see is a wonderful fit between the data points, which I think you can see, and this theoretical line. And that theoretical line is based on models coming out of inflation. So it's been an enormous success. Now I promised to emphasize, and now I come to that last point, there's much less to say about what we don't know than there is to say about what we know. But I do want to emphasize that in spite of the fact that we've been shockingly successful in understanding this data and building a theoretical model that fits it wonderfully, we are still also shockingly ignorant about some important things. So for example, although inflation is clearly very successful, we are still really in the dark about the details of inflation. We often talk about inflation, just to be glib, as if it were a theory. It's not really a theory. It's really a class of theories, or sometimes it's called a paradigm. But in other words, the actual details of inflation still remain to be understood. Secondly, I want to emphasize that although this picture that we're building of the universe clearly fits the data very well, and it's, I think, certainly essentially correct, it's not a picture that we understand. It's really a very bizarre picture that we are discovering that describes our universe. It's a picture in which 22% of the matter in the universe is what we call dark matter, and we can't identify that dark matter. And what's more, 73% of the rest is what we call dark energy, and we're really completely clueless about what this dark energy is. All we know is that it's essentially uniformly spread through the universe, and that it's basically this repulsive gravity material which turns gravity on its head and causes the universe to now be entering a period of acceleration very closely resembling the inflation that we talk about in the early universe.